Hi, I'm Grant Imahara, and Mouser and I are empowering innovation together. I've been ordering parts from Mouser since I was in college, basically their age. We're here at Carnegie Mellon University's Robotics Institute to take a look at some of their cutting-edge innovations in robotics. Now, while I'm looking around, I want to challenge you to share your ideas about the future of robotics. How can they help us now and beyond? Submit your ideas below, and you'll get a free t-shirt and the chance to see your idea on a future Spotlight episode. But for now, stay tuned. I'm off to find some robots. This is Marcel Hebert. He's the director of the Robotics Institute here at Carnegie Mellon University. And you guys have been on the cutting edge of innovation since when?
From 1978 is when the institute was created.
Wow. Now,
Quite
how
a
long
while
have
ago.
you been here?
I have been here about 30 years. In fact, actually 30 years. And in fact, I've been here about as long as this robot.
Okay, so what's this one?
This one is called the Terregator. It's a robot that was designed for autonomous driving outdoors. So in fact, this is one of the very, very first attempts at autonomous driving outdoors. Now, of course, it doesn't look like a car or anything. This was 1984. But this was one of the first attempts that we had here at CMU.
It looks like it's got these really fat tires. It looks like it's designed to be off-road.
Yes.
And I can see right here, this is a ring of ultrasonic sensors.
Those are ultrasonic sensors. However, this was not the set of sensors that was originally used.
Oh, really?
Now, originally it used a camera and a laser rangefinder, which in fact for its time was a very advanced device.
Yes.
Those devices are now commonly used on practically any robots that are out there, mobile robots at least.
That are self-navigating.
Well, let me show you another one here. So this is one extreme, 1984.
Yeah.
30 years later, this is a Boss.
I actually recognize this one.
Yes, you had some involvement with this.
Yeah, I was, one of my former co-workers and I were hosting this event. This is from the DARPA Grand Challenge, right? Yeah. Urban Challenge.
The Urban Challenge. The Urban Challenge. There were several DARPA challenges. This one is for the Urban Challenge, which involved driving on roads in traffic with other cars and so forth. Okay.
Yeah, this one did really well. This one won the competition, if I remember correctly.
Yes, and in fact, it inspired a lot of the work that is now going on self-driving car. And so you can see from one side of the high bay here to the other side, 30 years difference between the two. Yeah. This is what we achieved, basically.
Now, interestingly, I guess in those days, they didn't have GPS.
That's right. Well, there was GPS, but not the kind that we can use.
Not available to civilians. Yeah. And this has LiDAR. And it has, what else does it? It's got actually
it has
like half a dozen
it has radar, it has cameras, several types of cameras, standard cameras. Now, 30 years ago on the Terregator, some of those sensors existed, except they were not nearly as good, they were not nearly as affordable, or small and low power and so forth.
Yeah. Not only that, the processing power available then versus now.
Absolutely.
This does all the processing in real time on this vehicle.
Absolutely. Yeah. In fact, on the Terregator, I remember those days where we had a big cable going from this thing over there back to the building. This was a major logistical operation. This is all self-contained, of course. Yeah. And what that enables us to do is to do what used to not be possible, to do very complex processing of the visual data. One of the things that is necessary for this is that the vehicle, the robot, has to be able to see and be able to think. Right. It's not just a matter of making decision and driving the motors.
It's not just going to waypoints. It has to decide, is there an obstacle in there?
Exactly. And it has to do this very fast. Think how fast you have to do it in real life driving.
I've seen this thing drive. Yeah. And it's not like, it doesn't poke long. It drives very aggressively.
So this is a completely different kind of robotics, okay? This is something that we're very excited about, that people here have been doing for quite a long time. This is, by the way, this whole area is part of what we call the Field Robotics Center, which basically looks at robots in the field, in various tasks in the field.
Out in the environment as opposed to being in the lab.
Exactly. So this one really focuses on the what we call robotics science, or robotic science discovery.
Okay.
So this is designed for exploration, for example, exploration of desert environment, and perhaps as a prototype for planetary exploration.
Sure.
And its objective is to do science. In other words, take measurements, discover perhaps new minerals,
Soil samples.
soil samples, and so forth. And the idea, of course, is to be able to do exploration for a very long time,
And
be
hence-
able to navigate itself without human intervention,
Yeah.
perhaps be able to identify areas that are interesting from a scientific standpoint,
Yeah.
and be able to re-explore them, that sort of thing.
And so it's able to do this for a long time, and that's why you have the solar panels
Yes, yes, in particular,
to
yes.
maintain.
Yes. So those are the smaller robots. Those are also robots to drive outdoors. There's an interesting backstory for those robots. They were actually built for a DARPA project,
Yeah.
which was one of the early project, or one of the first projects exploring the use of machine learning together with perception with robots. So the idea is that the robots somehow need to learn how to drive.
Yeah.
Imagine you put a robot in a completely new type of terrain. It has to understand how am I going to drive on this terrain, okay? Given my sensors, cameras, and
Right.
lasers and all that. So this was a project to do this type of learning.
So it tries one way of driving and then decides, is this the most efficient way? And if not, then
Right.
it tries another way.
Exactly. So if I've seen, this type of color, shape, and so forth, I know from my previous experience that's probably an obstacle, that sort of thing.
Right.
Those are, again, robots for extreme environment. This is something called Icebreaker. And this is a robot, as you can see, this is a mean-looking robot. Okay?
Yes.
And this is designed to drive on a very steep slope.
Yeah.
So in particular, again, this is in the spirit of exploration robot.
Yeah.
So exploring volcanoes, for example, where you have extremely steep slope
Yeah.
with sand and things that
It's
are very
got
hard
and
to
it's
drive.
got it's got big tracks, but a low center of gravity.
Right. And the
a
thing-
lot of surface area for
Exactly. And the thing it has in the middle, you see this pole here, is something that can be actuated and descended into the ground in
right.
desperation, basically, so that you can, for example, turn in place on an extremely steep slope.
Oh, yes,
Okay.
you can like anchor
Right.
yourself and then turn.
So the challenges are very different, right? The challenges for Boss is to drive in traffic and interact with this very dynamic environment.
Yeah.
The challenge for Zoe is to be able to do exploration over
Yeah.
very long duration. The challenge for this guy is to be able to drive on extreme terrain.
Right. So these are all same theme of exploration
Yes.
and innovation,
Yeah.
but different terrains, different environments.
So let me show you an extreme case of exploration. Now this is an early prototype, okay?
All right. What is this? What are we looking at here?
So we're looking at a robot that is designed to go on the moon
Okay.
and do some exploration. This is part of the what is called the Lunar X project,
Yeah.
where a robot is supposed to land on the moon and explore for about 500 meters on the moon. So of course this is a particularly challenging project
Yeah.
because obviously the remote aspects of the environment are particularly difficult.
Right. Right.
And you can see the same components as you see on all of the robots, right? You
Yeah.
have mobility components.
Yes.
You need to design everything that moves correctly for the environment. You have some vision component. The robot has to see, so you
Yeah.
still have
For
cameras and things
navigation.
like this.
Yes.
And you have inside, of course, computing and intelligence. So
Right.
you always have those three components in all of those robots.
Cool. And this one has a communication aspect.
Yes, of course, yeah. Now again, what you're looking at here is an early prototype design.
Yeah.
The real thing, actually, which should be at the center here, is actually a way for demonstration today. So unfortunately, you won't get to see it today.
You're running it through trials as we speak.
Yes. This is a robot that is designed for testing basically high-speed driving on rough terrain. Okay. Depending on, so some application call for larger robots, as you have seen some of those, especially the ones that have to carry people. Some robots some applications, call for very small robots. This is an example of that, very small and very highly capable.
Yes.
So this is one of those. We also have robots that are even smaller, that have shapes like snakes and things like
really?
that.
Can we see one of those?
Yes, you can, of course. As an aside, in this particular area, the field robotics, we're looking primarily at tracks and wheeled robots.
Yeah.
Because of the nature of the applications. But they can come in many different shapes, and snake is one of them.
Sure. If you're, say, doing, I don't know, rescue or something
Rescue,
like that.
exactly, mine, exploring things like pipes, sewers, things like that, of course. Yes. So this is not a robot, but it illustrates some of the more mundane things that have to be done here. You know, some of this has to do with very, how can I say, flashy or sexy artificial intelligence and
I'm glad that
things
we
like
agree
that.
that that's flashy and sexy.
That's flashy and sexy. And then there are other things that are a little bit hidden that people don't necessarily realize. So for example, doing testing of the components under very harsh conditions, like vacuum testing.
Right.
Okay.
Extreme temperatures.
Extreme temperature and all that.
Yeah.
So in terms of engineering, it's actually very important because people have to realize that to do this kind of thing, you need basically all the aspects of engineering, all of them. It's not just advanced computer science or AI. It's not just basic mechanical design. It's everything. So this is a test bed. Now again, this does not look like a fancy robot or anything, but the problem is if you want to design a robot that has to operate in a particular terrain, particular soil type, etc., you need to, of course, test that your design can operate in that environment.
Sure.
So this is a test bed to test soil interaction. So basically interaction between wheels and tracks and so forth on different types of soils and do actual measurement and things.
You got a bunch of different types of wheels over there.
That's right. So we have also outside agencies and lab who ask us to test their design and so forth. So this is just to show you some of the, things that go behind the scene, basically, in building and designing those robots.
Nice. Everything here in the field robotics lab is covered in dust of different kinds.
Yes.
These are robots that get out in the world.
Yes, and many of those robots actually, at least in the center and in the Robotics Institute in general, I've traveled basically all over the world.
Yeah.
and sometimes in very difficult environment, in deserts and things like that.
So Marshall, I hear that some of your work has inspired a movie, is that right?
Yes, absolutely, absolutely. And you know what? I'm not going to tell you any more about it.
Okay.
I absolutely need to let my colleague Chris Atkinson tell you all about it. And I certainly would never steal the limelight from him. So
okay, well let's go talk to him. Yeah.